Concrete, a building block, a solution to large-scale construction projects, bridges, dams, and nuclear plants. But concrete starts cracking after you pour it. ASR, or alkali silica reaction, is a major degradation mechanism often called the cancer of concrete. ASR forms a gel that absorbs water and expands and does its damage over time on the surface and deceptively deep inside concrete structures. To study this process, scientists at Oak Ridge National Laboratory, the University of Tennessee, Knoxville, and a consortium of other universities have embarked on a large-scale, long-term research project utilizing a top-rate facility at UT, the John D. Tickle Engineering Building. The experiment involves building 3 large concrete specimens, each about 3.5 meters long, 3 meters wide, and 1 meter thick, containing thick rebar and embedded throughout with acoustic emission and pressure sensors, fiber optics, and transducers.
So we've got the 3 concrete specimens. One is confined, preventing it from expansion in one direction. We've got one unconfined reactive specimen, expanding in all 3 directions, and then we've got a control specimen to base all of our measurements off of.
Well, these structures are very typical in the thickness of nuclear power plant concrete structures. Most other concrete structures are typically thinner. For transportation applications, you're talking about 8 to 10 inches, and in a nuclear application, you're talking about a meter thick or more. These specimens are a meter thick.
This experiment is truly unique. That's probably the first time that we put up an experiment at that scale with so many monitoring sensors.
We've got multiple types of sensors. We've got sensors in the concrete, sensors on the surface. All of these are hooked up to 4 different data acquisition systems. And the systems on the surface themselves measure strain, deformation.
And all these monitoring data coupled with non-destructive testing will be really helpful to decide what non-destructive evaluation makes sense and is actually viable and operational to be implemented in the field.
You want to test the structure without completely damaging the structure, so you want to examine things without being intrusive or creating any permanent damage. That's called non-destructive evaluation. So digital image correlation is an optical technique where we take images of any object or structure of interest in this case, and over a period of time, and then we compare these images to a reference image.
We use acoustic emission sensors, and the acoustic emission sensor is essentially a little piezoelectric element with a preamplifier in the sensor. And we have, in each specimen in the lab, they have 3 embedded acoustic emission sensors that are already cast in the concrete. And we have 4 surface-mounted acoustic emission sensors.
It takes 2 years to cure the specimen inside a chamber. When I say chamber, we're talking about a large-scale chamber, about 52 feet long, 30 feet wide, 12 feet high. Inside the chamber, we need to control the temperature and humidity over 2 years time span.
The environmental chamber is kept at a constant 100 degrees Fahrenheit and 100% humidity.
Now, in this condition, the reaction is accelerated, and under normal circumstances in a real-life scenario, this would occur 50 years, maybe 50 years in a nuclear power plant.
In this project, we're doing everything that we can to make our concrete as representative of how ASR develops in the real world, as opposed to being an ultra-accelerated laboratory experiment. Making a reactive mixture is pretty easy if you have the right aggregates. If you start with a highly reactive aggregate source and then add alkalis to the mixture, and in this case it's in the form of sodium hydroxide, and basically providing as much fuel for the fire as possible. Or in some cases, with respect to this project, we're actually dialing that back a little bit so that we don't see too much expansion too quickly.
Ready Mix Concrete, the concrete mix supplier, is less than 2 miles from the Tickle facility.
Fortunately, it's been a cooperative effort with multiple universities, and our opportunity to work with Tennessee to be a part of such an experiment gives ready-mix producers the opportunity to experiment with this so that in the future we have a much better working knowledge with these particular pours, mixes, and all the aspects that come along with it.
I need a classic, a group of dedicated personnel, because I cannot do it myself, because we're talking about large-scale structure. Give you an example, to change one of the boundary conditions of one specimen, it takes 50 tons of steel to confine this thick concrete slab, and weigh 50 tons.
The dedicated personnel spent a long, hard, and hot day pouring the concrete in the 3 forms.
So this is a great opportunity for our students to work on a really big problem with a world-class team. They may not get another opportunity like this in their lives, so this could be a landmark opportunity in their career. They're going to write their master's theses, their doctoral theses, research papers based on this research. And they're also getting experience in planning and executing a large, complex project. And that's a skill very valuable to civil engineers that they'll be able to take with them into the workplace. We're in the knowledge business, and this is a great opportunity for us to contribute to knowledge related to civil engineering infrastructure, to develop infrastructure that is safer, smarter, and more sustainable.